This conference will now be recorded.
Hello everyone. The topics we will discuss today: significance of Heisenberg uncertainty principle, quantum mechanical model, reason for failure of Bohr's model, Schrodinger equation, features of quantum mechanical model, then Schrodinger equation for hydrogen atom, and if time permits, quantum numbers, and also some problem. Significance of Heisenberg uncertainty principle. So this principle we have already discussed, and now we are going to see some important points related to this principle. Okay, now we know, according to this principle, we have also discussed some problems related to this, that simultaneously we cannot measure the exact position and exact velocity for electron or any subatomic particles. Fine, but why this principle is so, that is why we cannot measure exact position and exact velocity simultaneously, why it is so. That means the question here we have, how this principle actually works. Fine. Remember, just suppose you want to measure anything, not necessarily it has to be electron. Fine. That is the position of electron. So when you are trying to measuring something, you need some meter stick, and the graduation of the meter stick, it should be such so that the object that you are going to measure, it is suitable for that. Okay, so the graduation that is present in the meter stick, that must be lesser than the length that you are going to measure. Fine. Now when it is, you are applying the same principle for electron, that is, you are trying to determine the position of electron. Okay, now as its size is very small, it is microscopic particle, so obviously the meter stick for measurement of the position of electron, that must be such, that is, it must be calibrated in such a way that it is suitable for the dimension of electron. That means the calibration in it, that is the calibration units, the smallest unit, that must be smaller than the dimension of the electron, then only you can measure this. Now as electrons are very small in size, so when we are using light for knowing its position, you are using light means there is some specific wavelength, and wavelength must be very small. This wavelength, it must be very small, because as it is mentioned in the previous point, that the meter stick calibrated in units of smaller than the dimension of the electron. So wavelength must be very small, and when wavelength is small, that means energy is very high. So we have to illuminate the electron with that light which is having very small wavelength. Okay, then only we can have this proper meter stick for the measurement of position of electron. Okay, now when I am saying that it is very small wavelength, so according to this equation, that is momentum is equal to h by lambda, Planck's constant divided by wavelength. Now when lambda is very small, h is already constant, so the denominator is very small in the right hand side of the equation. That means this wavelength will be very high for the light that you are using for measurement of the position of electron, because lambda has to be small, and when lambda small, mv is very high. So this high momentum photons of this type of light which you are using to illuminate the electron, basically you are using this light for the determination of position of electron. So this high momentum photon of such light, it will obviously change the energy of electron during collision, because you are illuminating this electron with light, so there will be some collision, and as it is very high energy light, that is high momentum is present, that is the reason now the photons of such light would high momentum of this light, it will change the energy of the electron. Okay, so when energy is changed, obviously now you can understand how the Heisenberg uncertainty principle is work. You are using this light, that is fine, and by using this, obviously we will certainly be able to calculate the exact position of the electron. But because of this collision of high momentum photons, because of this collision, we would know very little about the velocity of the electron. Okay. Similarly, when you are trying to measure velocity, obviously now you can use high wavelength, that is low momentum photon. But when you are using low momentum photon, lambda is very high, then you cannot measure exactly the position of electron, because now the condition that must be present, that is to measure anything, the meter stick calibrated, the meter stick graduation, it must be smaller than the dimension of the object that you are trying to measure. Okay, so how this principle works, this is the answer. So when you are using small wavelength, that is high momentum light, it is true that you will be able to calculate the exact position, but you will have very little idea about the velocity of electron. There will always be some error in the value of velocity that you are determining, and vice versa. So in this way, this principle works. Next, we have another question. Why this principle rules out the existence of definite path or trajectory of electrons or any similar microscopic particles? We know that Bohr's model, we have the idea of specific path, that is definite path or trajectory for electron. Electrons is moving through this trajectory. Suppose this is the nucleus. There is a fixed path like this, circular path. That means there is a definite path or definite trajectory for the electron. So electron is moving through this path. But actually this model, we have seen there are some limitations in Bohr's model. So this type of definite path or trajectory actually doesn't exist. And it is also ruled out by this Heisenberg uncertainty principle. So why this principle is actually ruling out the existence of definite path? That is the question here, and we will try to find the answer. The fixed path of an object, how you can determine? It can be determined when its location and velocity at various moments is known. Okay, so fixed path, because it is electron is not that is, it is not fixed, its position is not fixed at any particular position. It is always rotating, it is moving, it is in moving condition, right? That means if we want to know the fixed path, you have to know its location at a particular moment, and also after some time what will be its location. Then only you can understand the trajectory through which it is moving. So the location and velocity at different moments, these informations we must have if we are predicting this fixed path. Now, if we know where a body is present at a particular instant, and also its velocity, also the forces that are acting on it at that particular instant, then only you can predict what will be the position of that particular body after some time, because you are trying to predict trajectory. So you have to know with change in time, what is its next position. Suppose after 5 minutes, what is the position? After 10 minutes, what is the position? So if we know where a body is present at a particular instant, along with its velocity and the forces acting on it at that particular instant, then only you can predict where the body will be present after some time. Then only you can know the trajectory. But we have already seen that based on Heisenberg uncertainty principle, we cannot do so. So you cannot determine its location as well as velocity simultaneously according to this principle. So that is the reason, according to this principle, that is Heisenberg uncertainty principle, for microscopic particles such as electron, it is not possible. Which is not possible? The existence of definite path or trajectory. This type of path cannot exist. Okay. So in this way, by applying Heisenberg uncertainty principles, we can rule out the existence of definite path. So according to this principle, for microscopic particles such as electron, we cannot know the exact position and velocity simultaneously, and that is the reason fixed path is not possible. Okay. One more problem based on uncertainty principle. A ball weighing 10 gram, it is moving with a velocity 90 meter per second. Uncertainty in velocity is given 5%. Velocity exact value is given 90 meter per second. Uncertainty is 5%. Now, from this information, you have to find the uncertainty in its position in this format. Gap multiplied by 10 to the power minus 33 meter. So this value is actually required. That is, there will be some integer. It should be rounded off to the nearest integer. Planck's constant value is given 6.63 into 10 to the power minus 34 joules second. Now, from Heisenberg uncertainty principle, how we express uncertainty? We express uncertainty in position in this way: del sign then x. So this is the range in which that is the position may vary. So this is the uncertain position. We have to find this value of del x. Next, we have to find what is the uncertain velocity. Exact value is 90 meter per second, but we have to find del v. So del v is 5% of 90. See how we can calculate del v? It is 90 into 5 by 100, 5%, which is 4.5 meter per second. Next, we have to use the equation for Heisenberg uncertainty, which is del x into del momentum greater than equal to h by 4 pi. So del x into del p. Now del p you have to break in this way, m into del v, because we know del v. We have to find del x. M is known because here mass is given in the question. And this total quantity, that is del x into del p or m del v, this is greater than equal to h by 4. So del v should be equal to h by 4 pi m and then del x. Now here m, you have to change the unit. Be very careful. Here m value is given 10 gram, but you have to convert it to kg. So this is equal to 0.01 kg. Be very careful about the units. All should be in SI. Now put the value of h, 6.63 10 to the power 34 joule second divided by 4. This is the value of pi, 3.14. This is the value of m, and this is del v that we have just calculated previously. So after calculation, you will find this value. Now you have to write here. It is already written in the format 10 to the power minus 33, and there is a value with it. So you have to arrange it in such a way so that you can compare with this format. And here, this is actually close to which integer? It is 1. So answer should be 1. And here, how the units, that is the final unit, it should be in meter because we are using SI system. So this is meter. But how we are getting this unit? See, joule second, that is the unit in the numerator. And the denominator, there is meter and there is del v. Now del v is velocity unit. That means it must be, sorry, mass is kg. So the unit of mass kg I am writing, and for del v it must be meter per second. Now if you break joule, it is actually kg meter square, then per second square. This is actually joule, and s is already there, divided by kg meter per second. Now per second, if you bring it to numerator, it will be s square. So all the s cancelled, kg cancelled, meter square divided by m. So ultimate unit left is meter, which is the unit of it is a position. Fine. So in this way, you can also understand how the units, final units we can get, which is the unit of length. Okay. So answer is 1. Reason for failure of Bohr's model. So Bohr's model is basically main reason is de Broglie concept. Another one is Heisenberg uncertainty. Fine. So according to de Broglie, dual nature of matter exists, but in Bohr's model we completely ignored that. In the wave character is not considered in Bohr model. Basically, it has ignored the dual behavior of matter. But according to de Broglie's equation, we have seen dual behavior of matter existing. So that is why this is the reason why this model, we cannot further extend this model. This is one of the reason. And the second point, according to Bohr model, we have seen an orbit is clearly defined path. That is, suppose there is nucleus, I am writing here positive sign, and there is a circular path which is fixed orbit, fixed path. But this path can completely be defined only when position and velocity of electron are known simultaneously. Otherwise, this type of path cannot exist, right? But according to Heisenberg uncertainty principle, we have seen it is not possible. You cannot determine position velocity simultaneously. So that is the reason, because of these two reasons, basically two reasons. One is de Broglie's concept, that is dual behavior of matter. We have ignored that in Bohr's model. And the second reason is Heisenberg uncertainty principle is saying you cannot measure position and velocity simultaneously. So definite fixed path not possible. So this orbit is not possible for electron. So these are the reasons why this model is not successful. So there is some previous model, if you consider, that is the older models compared to Bohr's model. Compared to that, obviously here we have some merits for this model, but we cannot extend it further. So to overcome all this problem, the advanced model, we are going to that after this failure of Bohr's model. So in Bohr's model, as you can see, there is some definite path. So these are the definite path, but actually it is known as orbit. But the new model, which is known as quantum mechanical model, here we do not use the term orbit. Now we use the term orbitals, that is cloud of electron. It is not a fixed electron. You can see here, you can see a single electron, but in the second picture there is cloud of electron, because we cannot predict the electron's position exactly according to Heisenberg uncertainty principle. Simultaneously, position velocity we cannot determine, and that is the reason this type of fixed path is not possible. So all you can do, maximum you can talk about the probability of finding electron in a particular space, and that concept is giving you a new term, which is orbital. Orbit is fixed path, which we use in case of Bohr's model, but orbital is all about probability, because you do not know the exact position of this electron with time. And not only exact position, I should say that position and velocity, because velocity means after some time what will be its next position, after by 5 minutes, after 10 minutes, what will be its position. So if you want to know with time how the electron is changing, that is exact position we cannot say, but all we can talk about is probability. So that is why this second picture you can see there is a cloud of electron, no fixed position. As there is failure in Bohr's model, we require a new model to describe structure of atom, which could account for wave particle duality, because this fact is completely ignored in Bohr's model. So we have to account for it. So this new model, it should account for wave particle duality of matter, and also it should be consistent with Heisenberg uncertainty principle. Now, the precision of the position and momentum of electron, that you can expect in case of Bohr's model, because in Bohr's model it is talking about fixed path, definite path. That means precision is there, but now there is no precision. If you apply Heisenberg uncertainty principle, precision is not possible. So maximum you can talk about probabilities. That is why the term precision is now changed with the term probability. And this new model came with this introduction of quantum mechanics. Okay, so now we will elaborate it. Quantum mechanical model. In classical mechanics, that is Newtonian mechanics, there we have seen that physical state of particle, that is defined by position and momentum. Momentum is mass into velocity. Now, knowledge of these two properties, it helps us to predict the future state of system. When you are only talking about position, at a particular moment right now, what is its position, that is fine. But when you also know the momentum, you can predict the future state of the system. After some time, what will be its position? That also you can predict. So knowledge of both these properties helps us to predict the future state of the system. Fine. Now, motion of objects that you see in daily life. Maybe it is a falling object or planets that are moving. So if you consider all this that we come across in our daily life, that you can describe very well simply by using classical mechanics. That is, Newton's law of motions are used. Mainly it is a physics, fine. And there you have considered only the particle-like behavior. Because when I'm talking about the daily objects you see in daily life, basically all these are macroscopic macroscopic object. Obviously here wave character is not so significant, particle character is mainly present. Fine. But according to Heisenberg principle, both these properties, which properties? Position and momentum. Both these properties cannot be measured simultaneously with absolute accuracy. And that is especially significant for microscopic particles, not macroscopic. So that is why for macroscopic objects that you see daily life, you can simply use classical mechanics based on Newton's law of motion. But for microscopic particles, the particles that are very, very small, now classical mechanics will no longer be applicable. Okay, because according to Heisenberg uncertainty principle, both these properties cannot be measured, and when cannot be measured simultaneously, obviously the future state of the system you cannot predict. Fine. As the classical mechanics does not consider the dual nature of matter, it doesn't consider dual nature of matter, that is fine with macroscopic object because their wave nature is insignificant. But that is significant when you are considering microscopic particles. Now you have to consider both wave character, particle character. So classical mechanics doesn't consider the dual nature of matter, which is significant for microscopic particles. So that is the reason classical mechanics fails to explain the motion of microscopic particles. And that is the reason now we need a new model, a new mechanics called quantum mechanics was developed based on this Heisenberg principle and dual nature of microscopic particles. These two factors keeping in mind, this new model is introduced. Now when this new model, it is true that it is mainly for microscopic, but if you apply it for macroscopic objects where wave-like properties are not so important, then also you can get the same result that you have already obtained from classical mechanics. So this model you can apply for macroscopic objects also, because for macroscopic objects, the results that you get mainly from classical mechanics, now you can get similar type of result because this new model, it is considering both the character. So that is why it is fine for macroscopic and also for microscopic. Though it is true that its introduction is mainly for microscopic particles where you cannot apply classical mechanics. If you apply it, you will not get correct result. So that is why we now have this introduction of new model, which is quantum mechanical model. Now, if you want to know this model, we have to understand Schrodinger equation. So he expressed the wave nature of electron in terms of a differential equation. When you will see this equation, you will see this equation is basically a differential type of equation. This equation determines the change of wave function in space, and that is depending on the field of force in which electron moves. So what is the importance of this equation? Because this equation will help you to understand the wave function and also the change of wave function in space, because now we are talking about probability. We do not know the exact position, exact momentum of the electron, so you cannot predict the future system, but this equation will help you to understand the wave function by considering the wave nature of electron, and it will be help you to determine this change in wave function in space depending on the field of force in which the electron is moving. So this mechanics is based on this fundamental equation which is known as Schrodinger equation. This equation includes wave-particle duality of matter also, as proposed by de Broglie. But remember, this equation is quite complex. We will just see the equation here, even you don't have to remember it. And how we solve this equation, that is really very high class mathematics. Okay, supercomputers are required for that. So we are not going to the detailed calculation of it. We will just see the equation and how from this equation we can understand the different energy of electron, different wave function of electron. That is the main part. But remember, this equation including wave particle duality of matter, which is proposed by de Broglie, it is very complex. Its calculations are very complex. Details of this calculation you can find in higher classes. So this equation for a system such as an atom or a molecule whose energy does not change with time, that means it is time independent. So this condition must be present. If it is you are applying for an atom or molecule where energy is not changing with time, that means energy is time independent. It can be expressed like this. Here you can see this term H. It is known as, this term is known as psi, that is equal to E into psi. Where H, it is a mathematical operator which is known as Hamiltonian. So this is the wave function and is a function of position coordinate of the particle. So Hamiltonian is basically this operator H, sorry, there will be comma, and psi on which this operator is applied, that psi is called wave function. So it is a function of position coordinate. Suppose it is electron, fine. So it is somewhere in space, and when it is space, you have to consider x-axis, y-axis, z-axis. So three coordinates you have to consider. So this wave function, here it is function of this position coordinate x, y, z. This equation can be solved only for certain values of E. So all the values of E are not allowed. So what it means? It means that the energy of the system is quantized. And the E term that you will see in this equation, that is actually total energy. When I'm saying total energy, you have to consider that in this atom there may be different types of energy. Okay, now different types of energy, I mean to say kinetic energy, potential energy, because different types of forces are actually operating. If you consider that in attraction between electron and proton, there is attraction. If you consider two similar charged particles like two electron or two proton, there will be some repulsion because it is similar charge. So considering all these different charge, different energy, this total energy is expressed as capital E, and this energy, all the energy values are not quantized. So this equation you can solve only for a certain values of E. That means the system is quantized. Now these permitted total energy values, they are known as eigenvalues, and the corresponding wave function, that is the psi, actually it represents atomic orbital. Remember the term that we use in case of Bohr's model, the term is orbit, O-R-B-I-T. But now there is no precision, there is only probability. So the term is changed from orbit to orbital, atomic orbital. So atomic orbital, but when we will discuss in detail the quantum numbers, you will be able to understand what exactly atomic orbital is, because here in atomic orbital only the electron can reside. So this wave function actually represent, that is the psi, it represent atomic orbitals, not orbit. So this is the equation, H psi equal to E psi. This is the main equation. But what is H? In short, it is H, but it is actually like this. Here you can see differential equation del squared by del x squared. Fine. So that is, it is differential equation, and V is potential energy. Now, if you now apply this H, this total quantity in this equation, that is H psi, That means now with each of these term, psi will be there. See, psi is there, and also with V, psi is there. And in the right hand side, it is same as this equation. Suppose this is equation 1, this is equation 2. So what is the difference? In equation 2, we have just placed the value of H, that is Hamiltonian operator. If you multiply both sides, the inverse of this, h square by 8 pi m square, but if you multiply both sides, inverse of this, so this side, left hand side, it will be cancelled, right? Negative sign will also be cancelled because you are multiplying with a negative sign also. And right hand side also, there will be 8 pi square m by h square. So bring that quantity in the left hand side. So now there should be this term present, 8 pi square me by h square, and that should also be present with v. So that is why we have taken this part common and then e minus v. So all the terms are now in the left hand side, and right hand side there is 0. So this is the final how the final equation looks. But again, I'm saying this is not required in your syllabus. Just if you are interested how this equation is, the final how it looks, for your interest, it is there. So here in this equation, if you see carefully, all these del square, del x square, del square, del y square, del square, del z square, all these are second derivative with respect to z or x or y. So this x, y, z, these are actually position coordinate. That is position. E is total energy, V is potential energy, and psi is wave function or Schrodinger wave function. Now this equation, it is for hydrogen-like system, but if you apply it for multi-electron system, that is for elements of high atomic number, now there will be some difficulty. The equation will become more and more complex. So for hydrogen, it is solved easily, but when for multi-electron system you are applying it, now Schrodinger wave equation cannot be solved exactly for this system. Now we have to take help of some approximation method, then only we can overcome this difficulty. Okay. Some features of this quantum mechanical model. The energy of electrons in atoms is quantized. It can only have certain values. The values that are allowed according to the equation H psi equal to E psi. The quantized energy of an electron is the allowed solution of this wave equation, and it is the result of wave-like properties of electron also. The exact position and momentum of an electron cannot be determined with absolute accuracy, that you already know. And as a consequence, quantum mechanics introduced the concept of orbital. The concept of orbit no longer exists. Now we have this new concept, which is orbital, which is basically three-dimensional space in which we can talk about the probability of finding the electron. That is where the probability is maximum. That space in 3 dimension, that is actually the orbital. Okay. The solution of this equation for the allowed energies of an atom, it will give you this wave function psi, and this psi is atomic orbital. The wave nature of electron present in an orbital can be well defined by this wave function, because it is wave function. So obviously wave nature can be represented by it. And all the information about a particular electron in an atom, that is actually stored in this psi. And quantum mechanics, it is such that it is able, by doing this mathematics, it is able to extract this information, whatever is stored in this psi. We can extract this information by applying quantum mechanics. Obviously higher calculation is involved, but we can extract all these informations. So that is why it is so much important. This wave function itself, that is this term psi itself, it is true that there is no physical meaning. It is just a wave function. But if you consider its square, that is psi square, or you can also write it like this, psi in bracket xyz, because after all it is a function of position coordinate. You can write it for simplicity psi square, but exactly as it is a function of xyz, so that is why it should be written like this. And there is a mod sign also, because it can be negative positive, but when you are taking square it will be positive always. So when it is simple psi, it is wave function, but when it is psi square, it is basically probability of finding the electron in a small volume dx dy dz. Now as I am saying small volume, so you have to consider dx, not direct xyz you can multiply, because when you are multiplying xyz it will be something very large volume, but when I am taking dx dy dz and then you are multiplying, you will get some small volume. So three positions are there. We know, suppose when you find the volume of any cube, you take the length of this cube a and you multiply a 3 times, so it becomes a3. Similarly, if you consider here a small volume in space, how you will get it? Obviously by multiplying dx dy dz around a particular point xyz. Now the probability of finding this electron in a small volume, suppose I am drawing here small volume. So in this small volume, the probability of finding the electron that you can get from this psi square or psi xyz square, and it is always positive. Okay, and if you consider this probability per unit volume, okay, probability per unit volume, that means now you are dividing it by this volume, because per unit volume, now it will be converted to probability density. So that is the difference between these two terms, probability and probability density. Remember, normal density, what is the definition? Mass per unit volume. Okay, so when you are talking about probability density, it is probability per unit volume. And chi square, as there is a square, it is always positive. Okay. So Schrodinger equation for hydrogen-like system, when it is solved for this type of system, the solution gives different energy levels, basically the possible energy levels, where the electron can be present, and the corresponding wave function is psi of the electron, which is, this wave function is associated with that energy level. So suppose energy level E1, then it is psi 1, energy level E2, then it is psi 2. So for each energy level, there is a specific wave function psi. So this quantized energy state and the corresponding wave functions, these are characterized by a set of 3 quantum numbers. And these 3 quantum numbers are principal, azimuthal, and magnetic. Now these quantum numbers, they basically arise as a natural consequence in the solution of Schrodinger wave equation for hydrogen-like system. Fine. So it is not that we have chosen these quantum numbers arbitrarily. No, it is the naturally when solving the equation, we are getting it as a natural consequence, as a solution. Fine. So these wave functions are a particular energy state that is characterized by these 3 quantum numbers. So these quantum mechanical results of these hydrogen atoms successfully predict all aspects of hydrogen atom spectrum. So we have talked about it, that is spectrum of hydrogen atom, where there is some phenomena that we cannot explain by Bohr model, but if you apply this quantum mechanical model, even those phenomena that we have not explained, we couldn't explain by Bohr's model, that also can be explained now successfully. The Schrodinger equation cannot be solved exactly for multi-electron atom, unlike hydrogen-like system, which is one electron system. For multi-electron atom, there is some difficulty, but you can overcome this by using approximate methods. Fine. For multi-electron system, the principal difference with single electron system like hydrogen. So what is the difference here? Why we are getting some difficulty? The principal difference is increased nuclear charge. So when it is suppose electron, there is a single proton single electron, right? So nuclear charge is only +1. But when it is multi-electron system, suppose atomic number 10, so now it is +10, number of protons increased. So now you have higher nuclear charge, increased nuclear charge compared to single electron system. And because of this, now what will happen? All the orbitals somewhat contracted. So that is why the results that you are getting from the Schrodinger equation, there will be some error. There exactly we cannot solve. So when the positive charge in the nucleus it is very, very high, the attraction for the outwards electron that will also be high. So because of this attraction, now this space where the probability of finding the electron is very, very high, this space will be contracted. So that is why the results that you are getting from Schrodinger equation, it is not exact solution, but by applying approximate methods, that is applying some assumption, we can get results. So now we will see different quantum numbers. So there are actually total 4 quantum numbers, but first these 3 quantum numbers which you are getting as a natural consequence in the when we are doing the calculation in Schrodinger equation. These 3 quantum numbers are natural, we are getting by natural consequence. So this set of 4 quantum numbers, actually there are total 4, so that is it is mentioned there are 4. These 4 quantum numbers together, they can specify energy, size, shape, orientation of an orbital where the electron is basically present, about all the electrons that are present in the system. So this is the definition of quantum numbers. It will help you to specify energy, size, shape, orientation of an orbital. Now energy that you can understand, but what is size, shape and orientation? If you have some doubt, it will be clear gradually when detail, that is one by one, we will see the quantum numbers. So how the size is dependent, shape is dependent, orientation is dependent, everything will be clear. Fine. So this is the definition of quantum numbers. Now when you are trying to specify orbital, then 3 quantum numbers, the first 3 quantum numbers are enough, but the 4th quantum number is required if you want to specify an electron. Okay, that is the significance of it. The 4th quantum number, that is actually not arising from that is the natural consequence of Schrodinger equation. No, from natural consequence you are getting only the first 3. The 4th one you are getting, it is arising due to spinning of the electron about its own axis. It is not that electron is spinning, it is revolving around the nucleus, but it is also spinning on its own axis. Fine. When Schrodinger equation is solved for a wave function psi, you can get only the first 3, and the 4th one that is arising because of spinning of the electron about its own axis. So here you can see it is the first, at a first glance we are having this information, but one by one we will go into the details. The first quantum number, that is a principal quantum number, it is denoted by small n. It can have values integer starting from 1 to 3 up to infinity. The second one is known as azimuthal quantum number, which is denoted by small l. Now l, how many l values are possible? That is actually dependent on the previous quantum number, which is small l. So l values can be starting from 0. In case of n, principal quantum number, it is not starting from 0, it is starting from 1 up to infinity. But when it is l, it can start from 0 and it can end at n-1, not further. So suppose if n is equal to 3, the possible values of l will be 0, 1, then 2, because 2 is nothing but 3 minus 1, that is n-1. So you cannot have more than 2, you have to stop here. Fine. So in this way you can understand, when you know the value of n, principal quantum number, you can easily understand what will be the value of azimuthal quantum number. Now the third quantum number, magnetic quantum number. It is expressed by ml subscript or simply m, and its value is dependent on small l. That is the previous quantum number. So how many values are possible? Starting from plus L up to minus L. So suppose if L value is 2, so start from minus 2, the next value minus 1, the next value is 0, the next value is plus 1, the next one is plus 2. So you have to stop here because see, it is starting from plus L. Actually, I have started from minus L. It is the same thing. You can say minus L to plus L or plus L to minus S. Both are fine. So you have to maintain these two extreme. In between all the values you can have. So when L is 2, ml values, how many you are getting? Total 5. So 5 ml values. Okay. Now the fourth one, spin quantum number, it is denoted as ms or capital S. It can have two values only, and it is not dependent on what is n, l or m. It can have either plus up or minus up, not more than that. Okay, so this is in a nutshell all the information related to these 4 quantum numbers, but one by one we'll go into the details of these 4 quantum numbers. The first one, principal quantum number, denoted by small n. So these quantum number actually represent energy level in which electron revolves around the nucleus. Okay, so see in the right hand side picture, though here in the picture it is drawn as if it is a fixed path, though we know it is not possible, but for simplicity, for our understanding, we have this type of simple picture, but don't think it is denoting any fixed path like orbit. No, it is not that. We are just trying to see the energy levels. That idea you can get from principal quantum number. So this number, it can have value starting from 1 up to infinity. Now when it is 1, we use this type of English letters, capital K. For N2 in pink color it is L, then N3 in green color it is M. So in this way, K, L, M, N, O for 1, 2, 3, 4, 5 respectively. Okay, so if I'm saying it is N shell, basically I'm trying to say N is 4. Fine. Why it is important to remember? Because in problem, suppose instead of saying N is 4, that is 4th energy level, if it is saying N energy level, you have to understand it is actually trying to mean N is 4. So that is why you should know what is the significance of these capital letters K, L, M, N, O, etc. The maximum number of orbitals in a shell, n square. So when suppose first energy level 1 square, that means only one shell is possible. And when n is 2, 2 square, that means 4 shells possible. Fine. So this is the number of shells that you can get by applying this n square. And in each orbital, maximum 2 electrons you can place. So that is why maximum number of electrons that you can accommodate in a particular shell, that should be equal to 2 into n square, simply the double of n square. Because if number of orbitals, suppose 2, obviously number of electrons you can place, it should be 4, like this. It is always 2 of n square. You can understand from this table. Suppose n value is 1, number of orbital will be 2. Maximum number of electrons you can place is 2. So we are basically applying this n square. When it is 2, it is 2 square, that means 4. And 2n square means 2 into 2 square, that means 8. Similarly 3 square, and 2 into 3 square, so it is 18. So in this way it will go on. So this n, that is this quantum number, will give you the energy of electron. So here it is expressed in this way, and the distance of the electron from the nucleus, Rn. So this value you have already seen. Remember, when we have discussed Bohr's model, we have seen it is 0.529 multiplied by n square. So this n is basically this quantum number. Then also you have seen the energy levels, we have used this type of small n. Now you can understand the actual meaning of it. It is basically this principal quantum number divided by atomic number. Unit is angstrom. Now this energy term that you are seeing here, basically remember in Bohr's model we have expressed the energy like this: 2 into minus 2.18 into 10 to the power minus 18, then z square n square. Okay, we have expressed this. But remember, this energy is for a single atom. But here look at the unit, it is kilojoule per mole. So this value that you are seeing here, if you multiply it with Avogadro number 6.023 10 to the power 23, then you will get the value of energy in per mole unit. That is for 1 mole, because in 1 mole there is Avogadro number of atoms you have to, sorry, Avogadro number of electrons you have to consider. Fine. So when look at the unit, if it is kilojoule per mole, then it should be value like this. So with this term minus 2.18 into minus 18, if you multiply Avogadro number and convert it to kilojoule, you will get value 1312.8. But it is basically the same value that we have already seen in case of Bohr's model. So from this energy you can understand, from this quantum number small n, you can find out energy, whatever is the unit, per mole, per electron, whatever it is. But it can give you the energy of the electron. That is the importance of it. It can also give you the distance, because if you know the value of principal quantum number, simply by using this formula and z value is required, atomic number, you can understand what will be the distance of the electron from the nucleus and also the energy of the electron. So these are the significance of this number. What are the information that you can get from this number? Everything is mentioned here. Next, we will go to the second quantum number, which is azimuthal, but you should also know the other terms that are used for this second quantum number. It is also known as subsidiary quantum number or orbital angular quantum number, because from this number you can find out orbital angular momentum. So that is why another name is orbital angular quantum number. Each shell, that is each n, there is one or more subshell. So each shell can have one or more subshell, and number of subshells, that is actually small n. Number of subshells in a particular shell is equal to capital N, where N is principal shell. Now N is principal shell, that we have already seen, and L, once you know the value of the small n, you can also understand what will be the value of small l, because it varies from 0 to n minus 1. Okay. Now 0 to n minus 1 means, suppose n is 2. Now how many L values possible? Starting from 0, 1, only 2 values possible, because if you write 2, the last limit is n minus 1, and n minus 1 is 2 minus 1. So last limit is basically 1, so you have to stop here. So basically when total number of that is n value is 2, maximum how many values of L possible? That is also 2. So that is what is written here, that number of subshell in a particular shell is equal to n, because when you apply this 0 to n minus 1, you can check it yourself. Fine. Subshells corresponding to different values of L that are represented by some small letter symbol S, P, D, F. That means when L is 0, it is S. When L is 1, it is P. 2 is D. 3 is F, and so on. So see, in this table, the different orbitals, that is different values of small l, the corresponding which English small letter we use, that is mentioned here. There is also G, H, but up to F is enough. Fine. Now if you apply both of these, that is the first quantum number, second quantum number, n and l both. So when n is 1, maximum 1 L possible. So see how we are writing it with subshell notation, 1s. So 1 is atomic orbital. When I'm saying, it means principal quantum number is 1 and azimuthal quantum number is 0. When n is 2, it is written 2 times because now 2 values of L possible. So when L is 0, n is 2, it is 2s because s is 0L. But when L is 1, it is 2p. So when n value is 2, you can have maximum 2 subshells. Fine. In this way, you can proceed and you will get all these subshells. So it basically defines the three-dimensional shape of the orbital. Now, what is the meaning of this line? S, P, D, F, all these orbitals, they are having different types of shape. So when it is S, it is spherical shape. When it is P, the shape is changed. When it is D, 4 lobes are there. For F, it is more complex. So that is why we are saying it defines the three-dimensional shape of the orbital. It can also be used to calculate orbital angular momentum. Fine. So because of electron have two types of motion: orbital motion, spinning motion. So when you consider orbital motion, you have to consider this angular momentum. Remember, linear momentum we say mv, but when it is angular momentum, it is mvr. So orbital angular momentum also you can calculate by using this expression. It is root over L into L plus 1 into h by 2 pi. So this is constant, Planck's constant, and pi is 3.14. But if you know L, suppose L is S, that is 0. So you can easily calculate it. It will be 0 basically. But when it is n is 1, just simply put root over 1 into 1 plus 1. So in this way, if you know L value, you can also calculate angular momentum. So these are the two quantum numbers we have seen in today's class. The next two quantum numbers we'll also see in the next class. Thank you for your time.